Hi, Assalamualaikum and a very good morning. So now we are doing chapter 12, which is amino acid. And in this chapter, there are going to be two subtopics altogether, which is 12.1, which is introduction to amino acid, and 12.2, which is the chemical properties. So in this video, we're going to focus on 12.1 first. Okay, and in this video, we're going to learn on how to draw the general structure of the alpha amino acid. And we're also going to change the name of a given amino acid, which is the common name, and change them according to the IUPAC nomenclature. Also, we're going to define the term Zwitterion as well as the isoelectric point, which is labeled as Pi. Last but not least, we're going to draw the structure of a given amino acid in acidic medium, in basic medium, and at isoelectric point, which is Pi. So without any further ado, let us start. So for amino acids are basically compound that possess yang mengandungi both the amino group, which is NH2, and the carboxyl group, COOH. Okay, and mostly all the natural amino acids are basically alpha amino acid, where it has alpha carbon that bonded to NH2 group and the COOH group, okay, which is the carboxylic group. So when you look into the general formula here, this is the alpha amino acid because it has alpha carbon. So the alpha carbon going to attach with the amino group as well as the COOH group here, which is the carboxylic group. And the R here is referring to the side chain, and R here can be hydrogen, alkyl, or even any aryl group derivative. Okay, and for the amino acid, they can basically join together into a long chain by forming NMAP bond or the peptide bond between the NH2 group of one acid to the COOH group of another acid. Okay, and this refers to the formation of the dipeptide or even polypeptide, where this is the part of the chemical reaction of the amino acid in order to form a polymer. Okay, so you're going to look more about this in the subtopic of 12.2. Okay, now we're going to focus on the nomenclature first. So for the nomenclature, it's basically the same process as what you have learned in the previous chapter. You're going to look into which functional group is the priority. So the functional group, the functional group that is the highest priority is the COOH, which is the carboxylic acid part. Okay, and we need to find the longest carbon chain, and then we also need to do numbering. Okay, but for amino acid, it will follow a kind of general IUPAC naming pattern where they're going to have a 2 amino something acid. Okay, so let us look into the example. Let's say if you have a glycine here, so the glycine COOH going to be the higher priority. Okay, COOH is higher in comparison to amino, which is below here. Okay, so the COOH going to be the parent name. So we do the numbering from the carbon, which is number 1, and then number 2. Okay, so because it have two carbon chain, so it's going to be ethanoic acid. Okay, and the substituent at carbon number 2 is the amino group. So it's going to be 2-amino ethanoic acid. Okay, and that is why they follow the general name something like this, because the 2-amino here going to be the same. What's different is this part here, and then the acid will also be similar. Now we're going to look into the next example, which is the alanine. So alanine, we need to convert that into the IUPAC name. So we have 1, 2, and 3. So 3 carbon refers to the propanoic acid. And then at carbon number 2 is attached with the amino group. So it's going to be 2-amino propanoic acid. Okay, still follow the general IUPAC name pattern, which is 2-amino acid here. So what's different is the carbon chain. Okay, now we're going to do valine. So valine will have 1, 2, 3. So can be this one or this one, doesn't matter. So 1, 2, 3, 4 here. So 1, 2, 3, 4 refers to the butanoic acid. And then at carbon number 3, they're going to be a methyl group. And at carbon number 2, we're going to be amino group. So we will write methyl first because it is further in the alphabetical order. And then we're going to write amino. So you're going to be 2-amino 3-methyl butanoic acid. Okay, so 2-amino here will still maintain, follow the general IUPAC naming. What's different here is the carbon chain, which is 3-methyl butanoic, and then acid here is still the same. Okay, so now let us look into the phenylalanine. Phenylalanine. Okay, so we have 1, 2, and 3 carbon, so it's gonna be a propanoic acid. And then at carbon number 3, it attached with a phenyl group, so it's gonna be 3-phenyl. And then at carbon number 2, it's gonna attach with amino group, so it's gonna be 2-amino 3-phenyl propanoic acid. Okay, so it's going to be 2-amino 3-phenyl propanoic acid. So still follow the general IUPAC naming here. Okay, so yes, doesn't matter how long is the carbon chain going to be. So you just follow the similar pattern where you have to find the longest carbon chain and name the substituent and do the naming. All right. So now we're going to do the drawing. Okay, sometimes the question gives you the general name, the common name, which is triunine, as well as the IUPAC name. So you need to be able to convert that into a drawing structure. Okay, so you know that you will have the similar pattern, which is 1, 2, which is the carboxylate group, as well as the amino group. So the amino is always at carbon number 2. So you know that you need to make another two carbon here. So it's gonna be 1, 2, 3, and 4. So this refers to the butanoic acid. Okay, and at carbon number 3, it's gonna be attached with the hydroxy. And at carbon number 2, it's gonna follow the 2-amino because it contains amino group. Okay. At the same time, you can also draw the skeleton structure if you want. So if I were to draw a skeleton structure, I will get 1, 2, 3, 4, which also refers to the butanoic acid. At carbon number 2, amino group. At carbon number 3, hydroxy group. So both are still accepted. Okay. And now, let's say you have a structure of isoleucine. So the IUPAC name is going to be 2-amino 3-methyl pentanoic acid. So if this one will always follow the similar patterns, and then you're going to make it, because you have 2 carbon here, so you're going to make it 5. So you're going to add 3 more, which is 3, 4, and 5. Okay, so it's going to be 5 carbons, which refers to the pentanoic acid. And then at carbon number 3, it's going to be attached with the methyl group. And at carbon number 2, it's going to attach with the amino group. Okay, at the same time, you can draw the skeleton structure. Doesn't matter as long as the concept is this true. So we have 1, 2, 3, 4, 5. So at carbon number 3, we have methyl group. And then at carbon number 2, we have the amino group. Okay, so it's still the same meaning, which is the 2-amino 3-methyl pentanoic acid. Okay, now we're going to look into some of the features of the amino acid. So amino acid here is basically will have a chirality center except for the glycine. So meaning of the chirality center means that it's going to attach with 4 different groups of atoms. Okay, and because when it attached with 4 different groups of atoms, they can rotate plane polarized light, and it is optically active compound. And each alpha amino acids can exist as a pair of enantiomers. So they are enantiomers to one another, and this need to be labeled. Okay, but this does not happen for glycine because glycine will have C, H, H, C, O, O, H, and NH2 here. So because it is not a chiral carbon, bukan chiral carbon. Okay, so this is just a general information to tell you. Now we're going to look into the zwitterion. So basically, uncharged neutral form of an amino acid does not really exist. Okay, what it means by that is that the amino acids can undergo an internal acid-base reaction in which the proton, which is the hydrogen, is transferred from the carboxyl group, which is the COOH, to the amino group, which is the NH2, in order to form a dipolar ion called the Zwitterion. So let's say if we have a neutral form of amino acid here, and R here can be any hydrogen or CH3 or any aryl group. Okay, so this is the neutral form that we usually draw for our structure. Okay, but what really happened here is that the amino acid will have the amino group and also the carboxyl group. So the amino group here will act as the base, and the carboxylic acid part will act as an acid. So they will undergo an internal acid-base reaction. So internal refers to the reaction that happens in the same molecule. Okay, so since the base, which is the amino, will have a lone pair, it's gonna take up the hydrogen from the carboxylic acid part. Okay, so if I were to expand the structure, I'm gonna get it something like this. So I'm gonna take the hydrogen from the carboxylic acid part and transfer the 2 electron to the oxygen here. Okay, and as a result of the proton transfer, what I'm gonna get is NH3 plus, because the NH2 has picked up one hydrogen, so it's gonna become NH3 plus, and the COO minus gonna be producing here because it loses one hydrogen. Okay, and this is the representation of the Zwitterion, or known as the dipolar ion, because it have both positive charge and the negative charge. And the overall charge here going to be neutral because the negative is being neutralized by the positive. Okay, and this shows the amphoteric properties of the Zwitterion, where it can act as an acid as well as a base. Okay, so this is the correct representation. For example, if we have our alanine here, so our alanine can also undergo the internal acid-base reaction, where the NH2 here will become NH3 plus, and the COOH here going to become COO minus. Okay, so this happens for the representation of the Zwitterion. Okay, now as mentioned, a Zwitterion is basically amphoteric. So the meaning of amphoteric is that it can act as a base, dia boleh bertindak sebagai base in the presence of an acid, and can act as an acid, boleh bertindak sebagai acid bila kehadiran base ataupun alkali. Okay, so now let us look into the acidic solution first. So in an acidic solution, the Zwitterion will act as a base, and it's going to accept a proton in order to yield a cation. Okay, so acidic ada C, it's going to produce a cation, which is the C again. Okay, so let's say if you have a Zwitterion here, so R here can be anything, can be CH3, H, or any derivative. So this is your Zwitterion. When it is an acid, it is in an acidic solution which has a proton or H3O plus. What's going to happen here is that the negative charge here going to take up the hydrogen from the H3O plus, and this is going to form C double bond O OH. Okay, and the NH3 part here going to be maintained, and hence you can say that the overall charge here is positive, which is the cation. Okay, and the byproduct here going to be water, because you have take up one hydrogen from H3O plus, which refers to acidic solution. Okay, and the byproduct here going to be water. Okay, so in acidic solution, Zwitterion act as a base. The negative charge will attack the hydrogen in order to form COOH, and then H2O going to be released by byproduct. And then the positive charge going to be the overall molecule charge, which is the cation. Meanwhile, for a basic solution, the Zwitterion will act as an acid. Okay, it loses a proton to form an anion. Okay, so this is your Zwitterion, which is CO minus and H3 plus. So now you have a basic solution. So basic solution, for example, NaOH. So you have hydroxide ions here. Okay, so the hydroxide ion here going to attack the NH3 plus, and as a result, it's going to become NH2. Okay, and the overall charge of the molecule going to be negative. So negative here refers to the anion, and the byproduct here going to be water. Okay, so acidic, just remember C, and then you will get the cation. Alright, and this is the summary of the equilibrium. So you know that at amphoteric, the zwitterion going to exist as positive and negative charge. So when it is at acidic condition, it will undergo protonation, where the negative charge going to attract hydrogen in order to form COOH. And as a result, it's going to be positive charge, where it refers to a cation in acidic solution. Meanwhile, in the high pH, which is at basic condition, it will undergo deprotonation, pembuangan hydrogen. So NH3 akan buang hydrogen in order to form NH2, and the overall charge here going to be negative. So it's going to form an ion in the basic solution. Okay, so protonation, cation dengan acidic, all the red color here. Meanwhile, for the blue color here is the anion in the basic solution. Okay, and another important stuff here is that the pH at which zwitterion is formed is not necessarily 7. It depends on the isoelectric point, Pi. Okay, so let us look into the Pi, which is the isoelectric point. So the isoelectric point is basically the pH at which the concentration of the zwitterion is at the maximum, and the concentration of both the cations and anions are equal. Okay, where there is no net charge. Okay, so zwitterion is electrically neutral, and each amino acid will has its specific isoelectric point. For example, alanine, dia punya Pi adalah 6.02. Untuk lysine, it can be 9.7. So it not necessarily 7. Okay, so to understand more about this, let us look into the example. So the Pi for glycine, which is 2-aminoethanoic acid, is basically 6.1. So we have to predict the structure of glycine at A, pH 6.1, B at pH less than 6.1, and at C, which is pH at greater 6.1. Okay, so for glycine, if you were to draw the structure, okay, so glycine going to have 2-aminoethanoic acid. So you're going to draw ethanoic acid first, which is 2 carbon, and then at carbon number 2 is going to be attached with amino group. Okay, 1 and 2, and then hydrogen here. Okay, so this is your glycine. Okay, so now we have to draw the structure of the glycine at pH 6 equal to 6.1, which is pH is equal to our Pi. So we can say that at pH 6.1, our isoelectric point will be equal to our pH. So the equilibrium will contain the cation. The concentration of cation going to be the same as the anion, and they're going to be no net charge. So we know that we are referring to our zwitterion. So we're going to draw our zwitterion at pH 6.1, and what we're going to do is we're going to make it as NH3 plus and our COO minus. So it will undergo internal acid-base reaction, where the NH2 going to pick up the hydrogen from the carboxyl group in order to become NH3 plus, and it's going to become COO minus here. Okay. Now we're going to do the reaction at pH lesser than 6.1. So when at pH lesser than 6.1, it will gonna happen at the acidic condition. So the net charge on glycine is positive, or refer to the cation. Okay, so at pH 6.1, it refers to the acidic solution. So bila the acidic solution, we have our H plus, so the negative gonna pick up the hydrogen, so it's gonna become COOH here. Okay, and it's gonna have an overall charge of NH3 plus, okay, which is a positive charge, which refers to the cation. Meanwhile, for condition C here, which is pH greater than 6.1, we can say that it happens at the basic condition. So the molecule become negatively charged. So dekat keadaan basic, which is 6.1, we have our hydroxide ion. So the hydroxide ion gonna pick up the hydrogen from the NH3 plus, and hence become NH2, and then it's going to be COO minus here being maintained. Okay, and because of it contain a negative charge here, it's going to become an anion. Okay, and here is the cation, and here is the neutral, which is at the isoelectric point is the same as the pH that it is happening. Okay, so I think that's all for today's video. See you again some other time. Bye.